Hello, my name is David Odell and I am a VFD, Variable Frequency Drive Specialist employed by Bory Davis Incorporated. Bory Davis is the ABB HVAC drives representative in the state of Georgia. We are introducing a series of videos concerning the ABB ACH580 Variable Frequency Drive. This video is about drive basics and is the first in a series of videos. Before we get into the technical side of the variable frequency drive, I just want to share with you the relationship between ABB, Bory Davis Incorporated, and the HVAC drives market. In 1981, a small drive manufacturer in Orange, Connecticut, developed and introduced a variable frequency drive specifically designed for the HVAC market applications. That company was Parametrics. Parametrics contracted with rep agencies across the United States and provided exclusive marketing territory for them. In the state of Georgia, they contracted with Bory Davis Incorporated in 1981, 42 years ago. In 1984, Parametrics was acquired by ACH580, a large European electrical company that dated back to the 1880s. In 1988, ACH580 merged with Brown Boveri, another large European electrical company, and the company's name was termed ABB. In 1989, the factory in Connecticut was closed and full production began to occur in New Berlin, Wisconsin, a suburb of Milwaukee. It is there that the variable frequency drives for the Americas is manufactured even to this day. You can see from this slide the history of the HVAC drives manufactured by ABB. 6 generations over 42 years. Over those 42 years, Bory Davis Incorporated has maintained the contract with ABB as their representative to the HVAC market in the state of Georgia. This has several benefits. ABB is the market leader by far in the HVAC market in the United States of America. Bory Davis has knowledge and hands-on history with every ABB variable frequency drive generation. Bory Davis has structured their relationship with ABB to provide more than just typical sales and product awareness. They've invested in technicians that have been factory trained and certified to perform authorized factory startup, to provide warranty service with factory reimbursement. We have 2 VFD specialists like myself who provide phone support to our customers, provide training on the product like this video we're doing. We do that in the field. We can do it in person. We do hourly presentations for engineering or for contractors or for customers, lunch and learn type visits. And we also have the ability to do harmonic analysis, software analysis of the harmonics in the building. And we have the hardware. We have power quality equipment to be able to offer an on-site harmonic study using the real system. Okay, So we have a plethora of services that we offer to the customer, and it's all by calling one number, calling one company, Bory Davis Incorporated. Now you'll note in the slide here those 6 generations. If you look close, you realize that the ACH550 is a drive offered from 2002 to 2023. That's 21 years. That drive, which is the predecessor to the ACH580, covers half of all the time ABB has a drive offering for the HVAC market. It was a workhorse, and as we're going to learn, the ACH580, all care was taken to make it as retrofittable into the physics and the electrical considerations associated with the 550 series. So ABB continues to provide products that are amicable to the customers, present, future, and the past. So why use a variable frequency drive? Well, opposed to variable frequency drives, the way that you would vary flow would be with dampers, inlet vanes, or throttle valves. To begin with, we'd like to compare a starter to a variable frequency drive itself. You know, in the past, starters were used, and a starter basically is just applying all the voltage and frequency to the motor at once. And if you do that, and the motor nameplate says it's a 1750 RPM motor, well, as soon as you apply the 460 volts, 60 hertz to the motor, it's going to try and jump to speed, jump to 1750 RPM, and that's going to create a lot of inrush current. And that inrush current will be transferred to a mechanical stress in the system, which, if there are any small fatigue cracks in the impellers or the fan blades, it will begin to propagate those cracks, and eventually you'll lose your fan blades and you'll have maintenance consideration. Well, using the variable frequency drive will reduce that mechanical stress. I like to say in the classes we do in person, you know, when I was 16, my first vehicle was a 61 Studebaker Lark, and it had a V8 289 cubic inch engine with a 3-speed standard shift on the column, clutch, brake, and gas pedal. And my girlfriend and I would go to the basketball games in the winter in high school, and we'd leave the basketball game, go down to the local soda fountain place and have an ice cream soda or a sundae, and we'd go to leave, and I'd back out my 61 Studebaker, and I would push the clutch in, and I would rev the engine up to the red line RPMs, just like a 460 volt 60 hertz line being available, and I would pop that clutch, which engaged the engine to the transmission, and hopefully I would leave rubber on the road and you'd hear it, and I'd be cool because I just sped out and left rubber on the road. Some people weren't as lucky as I, and some people left their transmission on the road, because that abrupt connection of the engine to the transmission caused a lot of mechanical stress on that transmission. And that's what we're talking about here, is the mechanical stress associated with telling it to go full speed all at once. Okay, that's what the tires are supposed to do. They're supposed to relieve the issue by addressing the mechanical stress, just like belts on a cooling tower. If you hear them squealing, oh good, the tower started up. That's what you think, but really it's the belts are wearing out rather than hopefully the fan blades on the tower wearing out, or the gearbox if it's gearbox driven. So a variable frequency drive is like gently accelerating your vehicle, because it's going to start at 0 voltage, 0 frequency, and accelerate the motor to speed, which will gently accelerate whatever's connected to the motor, which is our load, our fan or our pump. So it reduces the mechanical stress in the system. Okay. Additionally, on deceleration, on stopping, a starter's just going to let go of the motor and it's going to coast to a rest. Well, if that's a pump that you're driving, you're going to feel and potentially you're going to hear check valve slamming, and that causes things to vibrate, and that also causes things to wear out. Okay, so with the drive, you can command the stop function to actually ramp the motor down from speed and let go of it once it gets down to 0 voltage, 0 frequency. Now, the other niceties of a drive is a higher efficiency, because I'm not turning on and turning off. I've got a system that varies the speed to maintain the comfort or flow or whatever you're trying to maintain in the system, as opposed to turn it on for a while and turn it off for a while, or waste energy across a throttle valve or dampers or inlet vanes. So we directly control the speed of the motor, which gives us fewer losses. And since there's no throttle valves, inlet vanes, or dampers anymore, those things that drop pressure and wear out, well, that's no longer the case. Okay, so reduced maintenance. And of course, the initial driving force in the market is that we save energy, which is money. Okay, power plants don't have to be built sooner because we're given the best energy saving in these applications out here. And these applications we're talking about are probably the largest energy users in the building we're talking about. Okay, so savings of energy and money, another big benefit you get with a drive versus any other method of trying to control the process. So just some starter versus VFD comparison. Here's a simple starter, and it's just a contactor with a set of thermals on the connected together. Well, the drive has thermal overload protection, and the drive sits between the power supply and the motor, just like a starter does. The drive starts and stops the motor, just like a starter does, but the drive starts at 0 voltage, 0 frequency, whereas a starter says 460 volts, 60 hertz, all ahead full right now. So that's that inrush concern. Each has motor overload protection, because you've got to protect your motor from an overload condition. We'll get to the seriousness of that in a minute. The drive can provide you with short circuit protection and ground fault protection for your motor cabling and or your motor. Okay, that's part of the protection you get with a drive, not always the case with the starter. The VFD also can communicate information to the building automation system. A starter generally going to tell you whether I'm on or off, and whether the overload's tripped maybe, the motor overload. The VFD can tell you if it's on or off, what speed I'm running at, what amps I'm drawing, what load. It can tell you what my carbon footprint is relative to what a starter would do. It can tell you how much energy you're using right now, or it can tell you how much energy you've used since it's been installed, or for the last 30 minutes, or for the last 30 days. A wealth of information you can get from the drive over a serial communications capability that you can't get with a starter. And of course, the drive gives you 0 to 60 hertz typical application, allowing you to run any speed from 0 to 60 hertz relative to generally some minimum frequency or minimum speed that is set by the application itself. But you only get one speed out of the starter. All ahead full, 460 volts, 60 hertz, nameplate RPM basically. So much more control with the variable frequency drive. So what is a variable frequency drive? Well, it's a device that controls the speed and direction of a three-phase AC motor. We drive three-phase AC motors, and we provide the torque and the resulting horsepower that the load requires. I've underlined and italicized load simply for this reason. Drives and motors are simple devices, really. They know they have to deliver what that load requires. If you put a 5-horse drive and a 5-horse motor on a 5-horse load, well, you're doing what's right by design. But if the load increases to 7.5 horsepower or 6 horsepower, well, that drive and that 5-horse motor and drive, they're going to provide 6 horsepower worth of torque and power, because they know that that's what the load wants right now. That's what the load requires. Well, that's why we put the thermal overload protection in there, because we got to protect the drive, the motor from overloads, because the drive and the motor are just delivering what the load is demanding. A load could go up due to a bearing wearing out, or belts getting out of alignment, adding side loads to the system. So the load's gonna, if you're having a problem with motor overload, you need to go look at the load. So the load demands the torque and the horsepower. The VFD supplies the speed necessary to maintain the system design control of the pressure, temperature, or GPM, or whatever we're trying to control. The VFD delivers what the load demands, even if it's more than the motor can handle, as I just mentioned. For this reason, we have protective functions. There's a motor overload, overcurrent fault, over voltage alarm, and over voltage fault. Those are some of the, just a short list of them, but they're ones that I want you to understand so you know where to look to try and take care of them. The overcurrent alarm is not a shutdown. It's a statement of we're seeing too much motor amps being drawn, and we want to keep the application running. So what could be causing this event to occur? Well, typically what might cause it to occur would be that we're trying to accelerate too fast. Well, the voltage and frequency signal is sent to the stator of the motor, and it creates a magnetic field, and the rotor tries to follow it. Well, if the load on the rotor is so big, a large inertia, that what we're telling it to do by coming up in a certain time period is more than it can handle, well, it's going to draw more current to try and make that happen. That might cause this overcurrent alarm. In that case, during that acceleration, the drive will simply stop accelerating and hover like a helicopter taking off. It goes to a certain height and says, oh, we got a little issue here. Let's sit right here and see if we can get this rotor to catch up to the stator. That should cause the current to go down, and we should be able to continue on our acceleration. So this is a alarm that tries to keep us running and the system online through a little bit of a transient event. The motor overload I talked about briefly, that is a fault that's saying the motor typically has seen 110% current for a minute. The VFD will fault and stop the system to protect the motor from burning up. This is a time overload. This isn't something that just bang happens. This is typically like a bearing is wearing out, as I mentioned earlier, which starts to increase the load on the system and eventually makes it no longer in the design of the system. Well, the protection has shut you down, but it's telling you, you better go look at the motor's load. Something's changed there. The overcurrent fault is an instantaneous trip saying the VFD just saw 250% current. This isn't like a motor overload. This is like a wire fell out from underneath a wire nut in the motor and winding connection and just hit another phase or hit ground. You'd get an instantaneous high current, and that would cause that overcurrent fault. That fault is there to actually protect the IGBTs, the output semiconductors in the variable frequency drive. We're going to learn more about those later. But it is also something where you look at the output as possibility of having caused that issue. The overvoltage alarm is implying that generally that maybe we're seeing some generator action from the motor, similar to that overcurrent alarm. Overvoltage is not a shutdown. It's a statement that this load, we're probably trying to decelerate it, but the inertia is too high to try and decelerate it in the short time that you've got programmed in. Now, if that's the case, that rotor is going to turn that motor into a generator, and it'll generate energy into the drive, and that generated voltage will attempt to and will charge up the DC bus. And the capacitors in the DC bus are the limiting component that is subject to voltage stress. And hence we have to shut the drive down. This overvoltage alarm will try to take care of things without shutting down, but if it's unable to control the system, it will eventually shut off on overvoltage fault. The last item here is a start interlock 1 alarm. That is generally termed the safety circuit. Normally an application by default needs a safety circuit. Usually there's some kind of smoke, fire, freeze, or overpressure, or some sort of a safety circuit that says if we see this condition, if we sense smoke shut the system down, even though we have a run command, because we got smoke somewhere. Okay, so that's the start interlock alarm. There are some applications that don't even have a safety circuit, and that creates a little bit of an issue simply because the variable frequency drive is expecting a safety circuit to be wired into it. And so it comes ready to accept one, and if one isn't tied in, well, that's the same as saying the safety circuit's open. So if you don't have any separate safety circuit coming in, we're going to learn how to program that requirement for one away, because there isn't one in this application sometimes. A variable frequency drive performs this by controlling the voltage and the frequency supplied to the motor. So although it's called variable frequency drives, actually varying both the voltage and frequency together to keep that motor happy. Down here in the lower left-hand corner, we've got the drive as it looked, 20 horsepower in 1968, and how it looks today. In 1968, there were a lot of components inside there, because the components, the carrying capability was limited. So you had to parallel a lot of devices, so there were a lot of components in there. Now the drives are very compact because the current carrying conductors are much more efficient and can handle much higher current. So there's a lot of fewer components necessary to create the variable frequency drive. To vary the speed of a three-phase AC motor and maintain the correct amount of flux or turning force, torque, to the motor, the variable frequency drive will vary the voltage and the frequency at a fixed rate defined by the motor and the load type. Okay, so we're going to talk about a couple of different load types. The most common load application is classified as constant torque. That's your conveyor systems or your escalators or your hoists or your cranes. A constant torque means 100% torque is required at all speeds from 0 to 60 hertz. We're going to satisfy this load type first, and then we'll discuss the other load type, which is the variable torque load application. I think you'll see, if we can show reasonably that we can provide constant torque, then surely you'll understand we can provide variable torque, as you'll see. Variable torque. So we have to do a little math. Consider the torque, horsepower, and RPM, revolutions per minute. The equation defining torque mechanically is torque is equal to horsepower divided by RPM. Okay, torque is equal to horsepower divided by RPM. 1 unit of horsepower is equal to the power needed to lift 550 pounds 1 foot in 1 second. Hence the equation: 550 pounds 1 foot per second, 60 seconds in a minute. That's 33,000 foot-pounds per minute. Where'd it come from? Well, some people think it came from the old county fair. You know, when I was a boy, I went to a county fair, and they always had a horse pull. And it was always a slab of metal, and they loaded it up with weights, and they'd get their team of horses, and they'd slap them, and see how far they could pull them in an 8-second period. And they'd average it out and determine whose pair of horses had the most horsepower. Well, I think they did that on a well. They put a weight down a well and basically put a pulley at the top and tied it off to a pair of horses and pulled them and did the same type of situation. Let's have them pull for so long and we'll average out the pull and the weight they were able to carry. And then when they did that, it averaged out to the average horsepower is 33,000 foot-pounds per minute. Recall from the last slide that torque in foot-pounds is equal to horsepower divided by RPM times 5250. Well, the horsepower was given as 3,300 pound-feet per minute. And the 5250 is a constant. And what that comes from is that equation. The RPM side of that is revolutions per minute. So horsepower being 33,000 foot-pounds per minute divided by revolutions per minute. Well, a revolution is one circle, and a circle is basically, as defined below, 2 pi r is the circumference of a circle. 2 pi is an actual number, 6.28. Pi is a number, and obviously 2 is a number. So the RPM distance consideration would be the 2 pi times r. So the factor of 6.28 comes into every revolution, hence the denominator 6.28. And if we divide 33,000 foot-pounds divided by 6.28, you come up with the constant of 5250, which is used in the equation for torque. Now, if the base speed of the motor is 1800 RPM, that would be 460 volt, 60 hertz, 1800 RPM base speed, then if our pulley on our motor had a radius of 1.9 inches, which is 0.158 feet, then one circumference of the motor would be 12 inches or 1 foot, and we'd get 1 foot per revolution, and at 1800 RPM that would carry us out 1800 feet. Okay, so with that in mind, looking at this torque equation right here, torque equals horsepower times 5250 divided by RPM, a base speed 1800 RPM motor, that's where you put that value in. And if you divide that out, you get 5250 divided by 1800, that's approximately 3 foot-pounds per horsepower at 1800 RPM. Okay, and that power rating is the rating at the base speed of the motor, and the torque rating is the torque rating at the base speed of the motor. Here we have a circle, and in this circle, this is the same as a revolution of the motor. And the pulley on the motor has a radius. And the radius, if we laid it on the circumference over and over and over and over until we made one complete revolution, we would note there are 6.28 radiuses that can be laid out on to make one revolution or to make one circumference of the motor. That's what that means. That's where that 6.28 comes from. Solving for torque in the first equation here, torque equals horsepower divided by RPM times 5250. Or we could solve for horsepower, which is equal to torque times RPM divided by 5250. And if we just plug in that, let's just assume we're a 1 horsepower motor. Okay, well, the rotational torque would be equal to the horsepower, 1 horsepower, divided by, if we're using a base speed 1800 RPM motor, times 5250. If you do that math out, you'll see that we wind up with 5250 divided by 1800. That's about that 3 foot-pounds per horsepower. Now in the other equation, if we have horsepower as 1 horsepower, and we have unknown pound-feet and radius, well, the pound-feet times 1800 divided by 5250 is going to solve for horsepower. So if it's 1 horsepower, again, if we do the math, to clear this, we'll need to multiply both sides by 5250 divided by 1800. And that'll come up with about 3, which is, again, where the 3 foot-pounds come from. Okay. So the power, the horsepower, is the rate of doing work, and it's basically you can solve for it either way if you have the 2 values you need, the radius or the force or the horsepower, and of course the base speed RPM of the motor. So horsepower is the rate of doing work. So imagine I've asked you to carry a weight of 100 pounds. I gave you a 100-pound weight, and we were in a room, and the room's 100 feet long, and I asked you to carry the 100-pound weight 100 feet in 1 minute. If I asked you to do that, the load is 100 pounds. I'm asking you to carry it 100 feet, and I want you to finish in 1 minute. Well, horsepower is the rate of doing work, and work is force times distance divided by time. Well, 100 pounds is the load you've got. I'm asking you to carry it 100 feet, and I want you to complete it in 1 minute. If you do that, the power you will have delivered would be 100 times 100, or 10,000 foot-pounds per minute of power. Now that's roughly 1/3 horsepower. Remember, 33,000 pounds per minute was the definition of 1 horsepower. Now, in the second case, I'm asking you to hold on to the same load, 100 pounds, but this time walk half as fast, i.e. only take 2 minutes to get across the room. Well, if I take 2 minutes, I would be doing 100 pounds, 100 feet per 2 minutes. Well, doing the math on that, you can see that means you did 5,000 foot-pounds per minute of work. Well, you did half as much work as you did in the first example. And the reason for that is why? Well, it's because you were only going at half the speed you were in the first example. You only went 50 feet in 1 minute. And if foot-pounds per minute represents the power, well, you only did half as much work as you did in the first example. Well, you only needed half the power then, because power is force and distance per a rating of time. This is the beauty of the variable frequency drive and the constant torque application. The full power is only needed at the fastest speed the engineer designs the system for. At all speeds below full speed, the power required drops off linearly with the speed, just as we saw, because we're slowing down. We're carrying the same load, but we're taking longer to carry it the same distance. We're doing less work each time. That is the beauty of how a constant torque load works. Okay? And that we're going to see is the beauty of what a variable frequency drive can deliver. Okay? Here we are simply showing the different base speed motors. 3600 RPM, 1800 RPM motor, 1200 RPM, 900 RPM. And if you take that same torque equation, torque is horsepower times 5250 divided by RPM, and if we're just looking at a 1 horsepower motor, then the torque is equal to 5250 divided by 3600 if it's a 3600 RPM motor. You do that math, that comes out to 1.5 foot-pounds per horsepower. Now an 1800 RPM motor, you look at that, well, it's half the RPM rating of the 3600, but if you plug in the same equation, but now our divisor is 1800 RPM, well, that's 3 foot-pounds of torque, and you can look at these others and you see that the torque available goes up, and that is occurring because the motor choice base speed RPM is causing that equation to produce more torque for a given horsepower. In each case, per horsepower, there's the torque available based on the base speed RPM of the motor. So, and that's just saying the equation works. And the fact is, most applications utilize a base speed 1800 RPM motor. So most applications are calculated based on 3 foot-pounds per horsepower. That would mean a 1 horse motor would be 3 foot-pounds capable, whereas a 10 horse motor would be 30 foot-pounds. And a 100 horsepower motor would be 300 foot-pounds of torque available at the shaft of the motor. That's all this is saying. So a mechanical grasp of the torque equation we've developed. Now we have to change it to an electrical equivalent. So mechanically, torque equals horsepower divided by RPM, as we said, and there's a constant 5250, but I left that out just for purposes. So electrically, horsepower is equal to volts times amps times efficiency times power factor times the 1.73, which actually is the square root of 3. That's in there because this is based on a 3-phase power equation. Divided by 746 watts, because that's how many is a measure of energy that is more useful than horsepower. So there are 746 watts per horsepower. The denominator in the electrical equation, that would be RPM. RPM is equal to frequency in hertz divided by the number of pole pairs in the motor. So frequency, hertz, cycles per second, divided by the number of pole pairs, PP for goodness sakes, is the number of pole pairs in the stator, which is the stationary part of the motor. That's where the electrical signal, the three-phase AC of voltage and frequency signals are sent. The cables, the motor cables, actually tie the electrical system into the stator of the motor. Torque, electrically, in a three-phase AC system, therefore, is equal to volts times amps times efficiency times power factor times the square root of 3, 1.73, divided by hertz, frequency, times 746 watts per horsepower, divided by the number of pole pairs in the stator of the motor. So once you bolt that motor in place, if it says it's a 5 horsepower motor, well, that's what it is, 5 horsepower. It'll be, and it's rated 6.7 amps, then that's how many amps it can handle, 6.7. If the efficiency is rated 89.5%, well, that's basically what the efficiency is. If the power factor is 75%, then that's what the power factor is. It doesn't change that much. The square root of 3, 1.73, is a constant. It's always going to be a constant. And then our denominators, we have the frequency in hertz times 746. Well, 746 is constant. It's the number of watts per horsepower. And the number of pole pairs in the stator, once you bolt the motor in place, they're not changing. Okay? They're not changing. So you wind up with a equation that says torque is equal to volts divided by hertz, voltage divided by frequency. This is where that information comes from. You take a picture of the motor nameplate on startup and you gather this information right off the nameplate. There's the horsepower, 5 horse. There's the 460 volts. Make sure that's what your supply is. The motor's rated 6.7 amps at 460 volts, and it's a 1760 RPM motor. That, I know, means it has 2 pole pairs in it. Okay. The torque equation electrically is boiled down to, you want constant torque, you provide constant volts per hertz. So out of all that nameplate data you entered, telling the drive what size the motor was, it uses that voltage and frequency that you inputted or you just simply confirmed, because there are default data in the drive. That's set up and simply did division of 460 volts divided by 60 hertz and comes up with a solution of 7.66 volts per hertz. If I maintain 7.66 volts of increase or decrease for every 1 hertz increase or decrease in frequency to the motor, then I'll maintain a constant volts per hertz, which means constant torque is available. And if you couple that with what we did mechanically, carrying that 100-pound load 100 feet in 1 minute or 50 feet in 1 minute, you see that the power required is satisfied at any speed. And the torque is satisfied. This is what a variable speed drive is. It is a volts per hertz device. I would like to tell you it's only ABB, but that's the design theory for everybody's drive. They're all designed basically for a constant torque load to provide constant volts per hertz in order to affect that function. All right, so here we have the graph of what we've been doing mathematically. Horizontally here is the frequency in hertz. That is what we apply to the stator. As well, the voltage is on our vertical axis. The motor voltage, called terminal voltage here, relative to frequency. And the flux level, the torque available, is represented by this brown dash line. And the power, the horsepower, the power required is along this vertical axis. So let's look at this. When you snapped a picture of the motor nameplate and then you entered that data into the drive, you said it was 5 horsepower, 460 volts, 60 hertz, 1760 RPM. So, and engineers normally design for the 60 hertz rating for the top end of the speed range, because that's where the maximum power is available. Okay, that's where 5 horse is available. For all speeds and frequencies below 60 hertz, if we follow this 7.67 volts per hertz, which we will, because that's what you entered into startup data when you put 460 volt 60 hertz motor data in, well, that means constant torque is available, because volts divided by frequency represents torque. And this brown dash line represents the available torque, and you see for all speeds less than 60 hertz, full torque is available for the same reasons of those things we did earlier. Remember the load and the distance where I took the 100 pounds, or you took it, and I said walk across the room in 1 minute, and that took 10,000 foot-pounds of work. Okay, that was the power required in the application. And then I gave you the same load, 100 pounds, but said take 2 minutes to get across the room. Well, that meant in 1 minute you only went 50 feet. 100 pounds, 50 feet was 5,000 foot-pounds. So you only did half the work, but as you can see, if this is also the power vertically shown, only half of the power, 50% of the power was required. 100% is required at 60 hertz, 50 at 50% speed, 30 hertz, only 2.5 horsepower will be required. Now, in some applications, there is a desire to go above 60 hertz. Some balance, they do the test and balance and find out, if I could just get another 10% flow out of this thing, everybody be happy. Well, if you go and you look at reality of what's happening at 60 hertz, if you are not fully loaded at 60 hertz, i.e. if you're not 6.7 amps on a 6.7 amp motor, well, that means you don't need 100% torque to operate. Maybe you're operating right down here right now. Well, that means I could take that speed up, so long as I don't cross this torque line, I'll run satisfactorily. So we can increase frequency above 60 hertz and run the motor faster, but we have to realize right here at 60 hertz, there's no more horsepower available. If it was 5 horsepower, well, this is where I'm getting 460 volts. at 60 hertz and whatever the load is, well, that's what I am. If I go up to a higher speed, then what I really see is the bottom of this equation is increasing and the top is constant. I don't have any more voltage and current to give. So I'm what's called constant power. And when I'm constant power, the torque available is dropping off. And if the operating point were to go above that torque available, that motor would slip out and we'd be done. Okay, we wouldn't be able to run the application. So it's all engineered to stay down here when you go above 60 hertz, and that is a caution about going above 60 hertz. You have to make sure you've got the energy available right off the nameplate of the motor. Now here in the United States of America, we generate power at 60 hertz, which is 60 cycles per second. That means 60 complete sine waves will occur in 1 second period here in the United States on the power lines. This gentleman, Henrik Rudolf Hertz, proved electricity can be transmitted in electromagnetic waves which travel at the speed of light and which possess many other properties of light. Okay, so this is something we're going to use a little bit later on as well. Electricity travels at some portion of the speed of light, is what he's saying. Well, that's fast. That's measurable too. I think it's 186,000 miles per second, something like that. Now, 60 hertz means 60 cycles per second. Well, that's great. And how many seconds are there in a minute? Well, all across the world, there's 60 seconds in a minute. So if I generate 60 cycles per second down the power line, and there's 60 seconds in a minute, well, that means I generate 3,600 cycles of energy per minute down the power lines in the United States of America. Okay. Over in Europe, they operate at 50 cycles per second. It's a matter of what your generators, however you're doing it, steam to electric, via nuclear, via coal. You're driving usually some kind of turbine to make that takes steam and drives up at 3,600 RPM, basically, which is 3,600 cycles per second, per minute. Right here we're showing you a sine wave. We're only showing you one phase. There would actually be 3 phases, and we'll see those a little later on. But we drive 3-phase AC motors, and the sine wave is made up of a positive alternation and a negative alternation of energy. And the time period, the horizontal axis is time. I mentioned the United States generates power at 3,600 cycles per minute. Well, that would be 60 per second. And if I looked at the beginning of one cycle to where it repeats itself, that amount of time, it represents one cycle, and 1 divided by time represents the frequency. And if I divide 1 by 60 hertz, I would realize that the length of time of this cycle is 16.6 milliseconds. 1 divided by time equals frequency. Now this is a simplified stator in a motor showing 3 phases, a phase A with 2 poles, B with 2 poles, and C with 2 poles. So this is a simple 2-pole motor, 2 poles per phase, A, B, and C. And if I say that this is the waveform for phase A being applied to the stator, then during the positive alternation here, A will be positive relative to A naught, let's call it, on the bottom pole. And that would cause the magnetic field to move around the stator from here to here. And on the negative alternation, this pole becomes positive and this pole negative, and that would continue to pull the rotor around this way. Okay, so for one cycle of input, one positive alternation, one negative, we get one revolution of the motor. Okay, that's a two-pole motor, and if you get one cycle of revolution for every cycle of input, you get one revolution. Well, you'd get 3,600 of them in a minute. That's a 3,600 RPM motor. Okay, that's what it's trying to say. The other thing is over here, again, the same sine wave. Same if I do the time base, the vertical amplitude on either is the voltage as it varies at the sine function. Okay, here is a four-pole motor. If you look closely, there's a phase A, and it comes in, goes through that winding, comes out, goes to another winding, and goes out at now I'm at 180 degrees going through the another winding, and then over here to 270 degrees, there's another winding, and then I come out the A naught phase right there, or A naught, other end of the winding connection. So this is a four-pole motor because there's four poles in the stator per phase. Okay, and that means also, since there's four poles to go through, well, when I put the first alternation in, it takes me basically from here to here. The second, the negative alternation, takes me from here to here. Well, I've only gone 180 degrees on the motor rotor, on the stator now. The third positive alternation takes me from here to here, and the fourth alternation takes me back to the beginning again. Okay, so it takes two cycles of input power to produce one revolution of the motor. That's a four-pole motor. It takes two cycles of input to create one revolution. Well, that's why that's a base speed 1,800 RPM motor. If there's 3,600 cycles per minute generated of the energy in the United States, and it takes two cycles to make one revolution on a four-pole motor, there you have it. But now, as you look at these motors, remember that torque equation we did the math on back there of the different base speed motors? Which one do you think has more pulling force? This magnetic field is what's pulling this rotor around. Do you think this one, or do you think this one, with twice as many poles as this one, is producing more pulling force? Well, I'm telling you that it's simple. Yeah, you got more poles, you got more pulling force working on that rotor to pull that rotor around. That's why there's more torque available. That's why that math equation we did on torque said that there was 3 foot-pounds per horsepower of torque available on a 1-horse 1,800 RPM motor, and only 1.5 on the 3,600 RPM motor. And then, of course, the applied frequency is 60 hertz, and the applied voltage 460. Okay. Here we have the actual, trying to share with you how the motor rotates. Now, I'm not going to go through this whole waveform, but down here are the 3 phases of AC. You've got an A phase, a B phase, and you show a C phase. Okay, and again, the vertical axis is amplitude, and the horizontal axis is time or frequency. If you look at phase B here, you see that it's beginning from 0, it's rising, falling to negative, and then here we are at 0 again. That time from 0 to where I repeat again is defined as the time for one cycle. And that time divided by 1 divided by that time represents the frequency or hertz I'm operating at. But now I want you to see, if we look at these three phases, at this moment in time, at time 0 here, it shows the A phase is somewhat positive uh, uh, relative to 0, and the B phase is actually 0, and the C phase is more negative than A is positive. So it sets up a field from A positive to A negative, and C positive or negative to C positive, and you see B has no potential on it. Those two fields will interact between A and C to position that rotor right there. Now, if we then look at time 2 here, A is at 0, so that's why these are 0. B is at almost fully positive, and that is B is north here to south here, and C is almost fully opposite negative, so C is represented there. So the field is created from C to B, and that moves that rotor from here over to here. And as we continue, if you looked at every one of these points, it's pulling this motor around in a clockwise direction. Okay, that's the way the magnetic field is rotating in the stator, and it's cutting the lines of force to the rotor, and the rotor's trying to follow it around. And of course, the load is attached to the rotor that's trying to follow this around, so that moves the load. Now, something to note in a pure three-phase AC sine wave system, if you add up all three phases at any point in time, they will equal 0. You see that B is 0 here. Well, C and A is positive as much as C is negative. The result is 0 volts. At step 2 here, you see A is 0 and C is or B is positive and C is equally negative. Well, at every point in time, if you have a pure sine wave, all three phases will add up to 0. That's going to become important down the road. You'll also note on this waveform that if B phase starts right here, crossing 0, that C phase is going to start 120 degrees later, and A phase will start 120 after that. Because a three-phase AC system, there's three phases, there's 360 degrees in one complete cycle, so between cycles has to be an equal number of degrees, so you phase shift things 120 degrees between phases to create that three-phase AC signal. You get 1 revolution per cycle of input on a 2-pole motor. Just as a side note, I thought this is pretty cool. Who knows which is true? I kind of believe the second item, but it's believed that there are 360 degrees in a cycle and a circle because the ancient Babylonians thought that was how many days occurred before the position of the sun relative to the earth repeated. They thought that was 1 year, one cycle of the earth. Okay. Another plausible theory is because the 360 is divisible by so many numbers, 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 18. That gives you a lot of math you can do with 360 degrees. I mean, let's face it. Why didn't they make it a circle 100 degrees? I mean, what's the difference? Pick a number. Why didn't you make it that many degrees? Well, I don't know, but this is a good plausible reason. Either one of them makes sense to me, but the second one really makes sense when you figure how much math these people were into. The Babylonians, they were very intelligent for their time. But there's no remainder. All these numbers divide with a point zero ending if you divide 360 by any of those numbers. That's pretty cool, I thought. Just to review motor speed, you know, the RPM I mentioned is 60 seconds per minute times whatever hertz it is. The power was generated at 60 hertz in the United States. That gives you the 3,600 cycles per minute. And then you divide it by the pole pairs, which is the number of stator pole pairs. So one pole pair is 2 poles. 2 pole pairs is actually 4 poles in a motor. So that's where you get the 2 pole pairs. You see 60 times 60, that's 60 seconds times 60 hertz. 60 cycles per second is 3,600 divided by 2 pole pairs. That's your 1,800 RPM motor. And we talked about those are typical synchronous speeds, but we don't drive synchronous motors. Okay. We drive induction motors. But there's the equation. Torque is pound-feet times RPM divided by 5250 would equal the horsepower. Okay. The rate of doing work would be the rate of the length over time and the load divided by 50. Reality is an induction motor, by its principle of induced voltage, does not operate at synchronous speed. There is a difference between the rotor speed and the stator rotating field, which comes from the drive. That difference is called slip, motor slip. And to calculate the shaft speed of the motor, it would be the 60 seconds per minute times the frequency. In this case, name-plated frequency is 60 hertz, divided by the number of pole pairs minus the slip. For a NEMA B design, the synchronous speed minus the rated speed divided by the synchronous speed would be the equation. So that would be, in our case of the motor we've been talking about today, it's an 1,800 RPM base speed motor, but the nameplate says it's 1760. So do the math on that, you get 40 RPMs is what the difference is, the slip. And if you divide that slip RPM difference by the base speed RPM, you come up with a percentage of base speed as slip. So that's how you come up with that. And our motor here is 1760. And what this means is, if you provided this motor with 460 volts, if you loaded it to 6.7 amps, okay, it would be running at 1760 RPM. So that's the full load rating at the motor. That's one point where the motor's happy. Now the fact of the matter is, rarely do you see motors operate at exactly what's on the nameplate. They may be running at 460 volts, 60 hertz, but they may be only drawing 3.35 amps of load at the speed of 60 hertz. Well, that's not the nameplate. Well, what does that mean? That would also mean that motor is not going to run 1760 because it's not fully loaded. That no load to full load slip, that's what that 40 RPM difference means. If this is only half loaded, then that slip's only going to be half of the slip. It'll be 20 RPM, and that motor will be running at 1780. And that's another reason why you need to understand motors don't run at their nameplate. Rarely do they, because people don't design things to run full loaded. But the fact is, the motor's fine. And if it's fine when it never even operates at its own nameplate, then surely it can find you can realize it'll be fine at all these other speeds too, based on the satisfied torque equations we've worked with, and the fact that this is just this nameplate is just telling you one exact point, okay, that this motor's designed for. So that if this motor fails, you could go find another motor. I'd assure you, unless you bought the exact same motor, you could go buy a different motor manufacturer. Not that I want you to, but you get a 5-horse motor rated 460 volts and 17, you'd say base speed 1800, and you bring that motor in, it might be rated 7 amps and 1755 RPM, and you'd be okay with that, and so would the load. Okay, so the nameplate is just for purposes really of one point of operation. When with the drive you get infinite points of operation. So the speed is a direct function of the applied frequency and the number of motor poles. Achieving the rated torque with rated current requires that the motor flux be constant and independent of speed, constant torque. Achieving constant motor flux requires the voltage and frequency be kept directly proportional to each other. That's your volts per hertz, and that remains equal to a fixed constant. The rotor slip is always less than synchronous speed because slip is required to generate and induce a voltage in the rotor. Yes, the rotating field has to always be cutting lines of force relative to the stator. If the stator actually ran in synchronous speed with the motor, it wouldn't run at all. It would just sit there. Okay. All right, so now let's look at the variable torque load. That's our centrifugal fans, centrifugal pumps, and centrifugal blowers. These are the commercial HVAC market drive load considerations. This is the key. These are what we drive. We've proven that we can drive a constant torque load. Well, now the simplicity of the variable torque load surely says we can drive a variable torque load. And I hope you can grab that quickly from these next. All right, so here are our centrifugal loads, and they operate by a unique set of laws due to the shape of the impellers. The laws are called the affinity laws, and they relate speed and pressure or torque and power together relative to speed. And this is where the big energy savings is. And if you think about the loads in a specific building, commercially, these are the largest loads in the building, your large pumps and fans, chillers, etc. Cubic feet per minute of flow, it says, is directly proportional to speed. So the flow rate is proportional to speed. It's the first law, which means I've given an example here, a 100-horse motor with a 460 volt drive, driving the motor at 460 volts, 60 hertz, is designed to deliver 100,000 CFM of flow. If I run at 100% speed, 60 hertz, I'll deliver 100,000 CFM. If I run at 30 hertz, 1/2 speed, I will deliver 50,000 CFM of flow. If I run at 15 hertz, 1/4 speed, that is, I'll deliver 25,000 CFM of flow. If I run at 45 hertz, I'll deliver 75,000 CFM of flow. The cubic feet per minute of flow is directly proportional to speed. They're a linear relationship. The static pressure or torque in the system is a square function. That is to say, again, at 100% speed, I'll need the full 100 horsepower out of the motor, and the torque required will be 100% squared. And 100% is 1, 1 squared is 1, so I'll need 100% torque at 100% speed. But at 50% speed, 30 hertz, delivering 50,000 CFM of flow, half flow, at 50% speed, the torque and static required will be 0.5 times 0.5 equals 0.25, 25%. So 50,000 CFM of flow, 30 hertz, 25% torque required, or static required. And finally, horsepower is relative to speed cubed. Again, if I need everything, I operate at 60 hertz, deliver 100,000 CFM, and 100% cubed is 1 times 1 times 1. 100% power is needed and available. But if I reduce the speed to 30 hertz and deliver 50,000 CFM of flow, I will need 50% speed cubed, which is 0.5 times 0.5 is 0.25 times 0.5 is 12.5%, 0.125. The energy, the power required to deliver 50% speed, 50% flow, is 12.5 horsepower on a 100 horsepower application. That is a lot of energy savings. Now, truth be told, an engineer that engineers a system in any building, the air system, he's going to design it for the worst day in Georgia in a decade. So that's what the 100% design is usually about. And the worst day in a decade in Georgia occurs just then, once in a decade. So it would not be unrealistic to believe that on a real day in Georgia, the other 99.99%, 80,000 CFM of flow would satisfy the comfort, creature comfort, and the loads. So let's look at 80,000 CFM. That would be 80% speed. 8.8 times 60 is 48 hertz. So at 80% speed, 48 hertz, 80% speed, the power required to deliver 80,000 CFM, 80% speed, is equal to 0.8 times 0.8, that's 0.64, times 0.8 is 0.5. 50% energy to deliver 80% flow, 80,000 CFM. You have a 50 horse load at 80% speed on a 100 horsepower system design. That's a lot of energy savings just ticking away as the clock rotates daily, going to the bottom line of the operation. And remember, these are the largest loads in the building. So that's a good deal. And that's why variable frequency drives are used on these variable torque applications. Here is the graph of what we've been talking about for the variable torque loads, our centrifugal fans, centrifugal pumps. Again, just like in the constant torque load, we're graphing the frequency along the horizontal axis and the percent flow or speed, the percent torque, and the percent power along the vertical axis. And what we see is this, this blue curve is the curve of flow. And we said flow is linear with speed, meaning at 60 hertz, we're producing 100% flow. At 30 hertz, we'll produce 50% flow. So we were 100,000 CFM design at 100% speed at 460 volts, 60 hertz, and will require 100 horsepower there. So there's where full power is required. That's why that's there, because this is the power requirement, this curve. The brown curve, just as in the constant torque load, is shown by the dashed brown lines here. But as you see, it's dropping away from 60 hertz at a square function. And so just as to show on this graph relative to the example stated, that last example given was 80% speed. 80% speed, if we multiplied 60 hertz times 0.8, we'd get 48 hertz. So we're right up along in here for 48 hertz. And following speed is linear. There's your 80% flow. So we're going to deliver 80,000 CFM of flow at 48 hertz. And the energy required to do that is this black curve. And if we come across here, well, that's only 50% energy. So only a 20% reduction in flow will save you 50% energy if we could purely follow this curvature of the impeller. And that's the graph of the power requirement. So you can see there's a lot of energy savings available. The other thing you can see is, remember the constant torque equation, you had constant 100% torque available from 0 to 60 hertz because you needed it. This application, we don't need constant torque. It's variable torque. It varies at a square function, as we discussed on the last slide. It's the only place where we know you need full load or full torque is at 60 hertz. At any frequency below 60 hertz, the torque's beginning to drop off and the power required is beginning to drop off. So that's why I said if I can show you we can satisfy a constant torque load, surely you can see we can easily satisfy a variable torque load. All right, so if the application requires torque to vary as the square of the speed, then you set the voltage to volts squared per hertz. This is a parameter in the drive, and it comes from the factory that way because that's our load requirement. Okay, and since torque is equal to volts per hertz, then we just do volts squared per hertz. Okay, so it will produce the square load function of the voltage for the load requirement. Okay, now I have to admit that I will, in many cases, change that to standard linear volts per hertz because linear volts per hertz gives me more breakaway torque down at the low end in case on a pump there's any particulate that settles in the impeller. That will cause a greater torque requirement at 0 speed than the pure centrifugal load with nothing inhibiting it. So that's just something that you might see that would manifest itself as a load that you try to start uh, and the load would just kind of sit there down near zero speed and draw a lot of current, mainly because it doesn't have enough voltage to break it free. Okay, so if I see that happen, that this thing is tripping out on overcurrent at very low hertz, like 1 or 2 hertz, that tells me that this thing doesn't have enough torque to break away, and I will change the volts per hertz to linear to give me more breakaway torque, and I'll share that more as we get into the drive section. Thank you. No, I'm not going to spend a lot of time on these next couple of slides, but I did want to just show you the math associated with torque and power versus speed, because torque is a relative to speed squared, which is volts per hertz squared. And if you do the math, this is just showing you what those voltages will be for certain speeds. So that's all I'm trying to say there. So here we're just bringing together the power versus speed relationship that I've already mentioned audibly, but here it is mathematically. 80% speed, 0.8 cubed equals 0.5 times your full horsepower equals a 50% energy savings with still only reduction of 20% flow. So, and the 50% speed and 25% speed given there as well. So we're about to end the first section here on drive theory. We'll do a little advertising. Again, we are Bory Davis. Since 1981, we've been the exclusive HVAC rep in Georgia. We're located there in Alpharetta. There's our website, our phone number, 770-242-0650. Bory Davis is proud to offer full service capability on all VFDs. We have the certifications for ABB on startup and warranty service, but we service other people's VFDs too. We're not authorized, but anything out of warranty. If you got people that have basically been in the business 42 years, we come across a lot of drives. So this is our service team, and Monty Monterdi is the service manager. He's a hands-on man. He's our licensed electrician. And then we have service technicians here. Those guys are out on the road all the time, providing training, warranty service, certification that they do, that they are certified on the drives. We have several videos on the ACH580 on our YouTube channel for your viewing that share many programming items associated with the drive. Please enjoy them. This is the YouTube site, or you could just Google Bory Davis YouTube videos and it would take you there. And with any questions that come up, don't hesitate to contact us with anything that arises out of this presentation, or any questions you have that you've just been thinking about and wondering a long time. Could be that we can answer them, and we'd be happy to. Our VFD specialists are one, myself, and two, Brad Templeton. Myself, I worked for that little company in Connecticut back in 1978 and left it in '84 to come down here and be their territory manager from '84 to 2011, and then I went to work for Bory Davis as a VFD specialist from 2011 to present. So I've got a history that dates back now too many years to remember, 45 years, I guess, in the business with ABB in one name or another in their variable frequency drives group. Brad Templeton, our other specialist, he came to us from an industrial ABB distributor. and prior to that, he worked with Baldor, their regional motors group right here in Alpharetta, Georgia as well. So he has a wealth of knowledge on drives and motors. Of course, I don't know if I mentioned it yet, but ABB, when they back in 2009, they actually bought Baldor, and so Baldor is part of an ABB group now. So they're both. If you're using Baldor motors, you're using an ABB motor now. And as a matter of fact, our ACH580 drive, the default motor parameters in the drive as shipped from the factory match the 4-pole base speed 1800 RPM Baldor Super E HVAC motor. So, and we are a distributor rep for those people too, for the Baldor motors. So we'd be happy to entertain any information you need on those as well. Thank you for your time today.